Part A. So what we could do with this, to add these two fractions, we can make a common denominator of that times that, which we've been told is x to the fourth plus 4. And then up top we're going to get that times that plus that times that, like so. And then that's 16 on x to the fourth plus 4, so you can cancel that from both sides by multiplying. You could also have done that from the start. You could have multiplied both sides by x to the fourth plus 4, and then you would get x to the fourth plus 4 divided by that, which we know from here is that, and then you'd get that divided by that, which makes that, which is what gives you that. So that's another way to get there. Now from here there's a couple ways you could do it. You could just expand this, or another way, you could just pick a couple values of x, like you can pick x equals 0, that would give you one equation, and then you could pick like x equals 1, and that would give you another equation. I'll just do it by expanding, and that gives us that. Now we can cancel a couple of things, because we've got a 2x cubed there, and we've got the 4x there. And then let's collect all the x squared terms. So we've got that one with the a, we've also got a minus 4 there, and a b, and another minus 4. Okay, so let's make that a minus 8. Okay, and then we've got all the x terms, so we've got a minus 2a, and we've got a plus 2b, and that's it. And then the constant terms, there's the 2a, and then there's 2b, and that's it. Okay, so from that, we know that this equals 16. So the idea here is that this has to equal 16 no matter what x is. So that means that that has to be 0, and that has to be 0, and that has to be 16. Because if these two aren't 0, then this is going to depend on what x is. So this will just give us 3 different equations. This one we can, so that equals 0, we can rearrange that to be a plus b equals 8. This one, you can rearrange that to make a equals b. And then this one, if you rearrange that, you actually get this again. So let's just solve those two equations. That'll just give us a equals 4 and b equals 4. So that's the answer. Part 2. Now I've got the result from part 1 in here because we're probably going to need to use that. So what we should do first is just plug this in. Now we found that a was 4 and b was 4 in part 1. Now we can think about how we're going to integrate that. And this one isn't too hard because we can work backwards from the answer that we're expecting to get. So let's think about how would we get that in the answer. Well, if we had ln of x squared plus 2x plus 2, and then minus an ln of x squared minus 2x plus 2, that would give that, because of the log laws, we can combine that into a fraction, and then when we plug in the m, that'll become that. So let's think about what the derivative of this is. This one would be 2x plus 2 over x squared plus 2x plus 2, because that's the derivative of that. But we don't have 2x plus 2 here, we have 2x plus 4. So let's think about how we're going to get a 2x plus 2. What we could do is split it up into a 2x plus 2 over that plus 2 over that. So that bit, when we integrate that, we'll get that. So that's great. And then we can do the same thing with this one. So the derivative of this bit is 2x minus 2. So maybe I'll make a negative 2x minus 2 up the top there because we've got a negative 2x there. And then, so we have to have another 2 over x squared minus 2x plus 2, so that that plus that equals that. But now at least we can integrate these bits. And then let's think about how we're going to integrate these. Again, it's not too hard because we can work backwards from here. So we're expecting to get like a 2 arctan of x plus 1. So let's think about what the derivative of that is. So that would be 2 times 1 over x plus 1 squared plus 1. Well, okay, that's great because that actually equals that. If you expand that, you get x squared plus 2x plus 1 and then plus another one, so that's great. And then this one will be x minus 1 squared plus 1. So actually what I might do is replace these with x plus 1 squared plus 1, and that one's x minus 1 squared plus 1. Now we know how to integrate each of these parts. So that one we get ln of x squared plus 2x plus 2. And then this one will be 2 arctan of x plus 1. And then, because of the minus here, we're going to get minus ln of x squared minus 2x plus 2. And here we've got plus 2 arctan x minus 1. Okay, and then we just need to plug in these. And then when we plug in the 0, we're going to have ln, that bit's all just 0, so it's ln of 2. And then we've got arctan of 1, which is pi on 4, so 2 times pi on 4. And then we've got ln of 2 again, so that actually cancels with that. And then we've got arctan of negative 1 is negative pi on 4, so 2 times negative pi on 4. And then that actually cancels with that. And let's simplify that minus that one. We can use the log laws to make that m squared plus 2m plus 2 over m squared minus 2m plus 2. And that's it. So this one, if you get stuck, you can always just work backwards from the end result. Part 3. So we just need to think about what's this going to equal as m gets really, really big. Personally, the way that I would think about this bit would be I would just sort of say m squared is a lot bigger than 2m plus 2 if m is really big. So we can just ignore these bits, they become insignificant. So it's just m squared over m squared, which is 1. But the way that they teach it in New South Wales is that we divide top and bottom by m squared. So you've got 1 plus 2 on m plus 2 on m squared. That's 2 on m squared. So, and then these become 0 as m tends to infinity, so you get ln of 1 on 1. But it doesn't really matter too much with this one. It's only a 1-mark question. You don't have to show a lot of working. So, however you want to think about it, you just get ln of 1 for that first bit. And then we've got arctan of really big number is going to be pi on 2. Remember, you can think of arctan as being, like, if it's at that slope, what's the angle? So we've got an infinite slope, which is like a vertical line. So what's the angle of that? Is pi on 2. And then for this one, you've got a really big number minus 1 is still just a really big number. So that's going to be also pi on 2. And then this makes ln of 1 is 0, So, and then you've got pi and pi, so we got 2 pi. Part B. So we want to know why EAD, which is this one, is equal to angle EBD, which is here. So let's draw that line in. Well, you can see that they're both standing on this arc ED, so we just need to state that. And you should also say what circle you're talking about, since there's 2 circles in the problem. So you would say something like angle EAD and angle EBD are standing on the same arc ED of C1. Part 2. So we're trying to show that this angle here equals that one. Now, if you can't see any direct way to get between 2 angles, what you can do is think like, what angles can I see which are the same as this one? And what angles can I see which are the same as that one? And try to find something in common. So with this angle, the ones that are the same as that would be like, you could look at what's standing on that same arc. So that would be EBA is the same as that. And then if you look at this angle in this circle, what's standing on the same arc? AC, well, that would also be this same angle. So they're both equal to this one in between. So you can set that out something like this. So you just got that AFC is the same as that one because they're standing on that same arc. Specify the circle since there's 2 circles. And then that's the ABC is the same as ABE. The E's up there. And then that's the same as EDA, which is that one because they're standing on that same arc. So that's it. Part 3. Let's just start this one by taking stock of where we've got so far and where we're trying to go. So in the past 2 parts, we showed that this angle equals that one, and also that it's equal to that angle in there. And we showed in part 1 that that is equal to that. Now, we're probably going to need to use those facts. And where we're trying to get to is we're trying to show that these points are concyclic, which means that you can fit a circle around them. And usually the way you show that is that you show that the opposite angles are supplementary. So like that one plus that one equals 180, or that plus that equals 180. So my thought process for this one was, let's focus on this pair of angles because we've already shown that that one equals something. So that's probably going to be better than using this pair of angles. And then I thought, okay, if I can show that that is supplementary to that angle, then that's what we need. So what's supplementary to this one? Well, this angle here is supplementary to it because they're on a straight line. So if I can show that that equals that one, then we'll have what we need. So let's look at this triangle here, and then this one is actually similar to this triangle because that angle is the same as that one because they're vertically opposite. So yeah, you can get that that one's equal to that one. And then I thought, like, what's the simplest way of actually showing that? And I ended up going with that this one is equal to those 2 because exterior angle of a triangle equals the sum of the opposite interior angles. And then that one equals that and that one equals that, so that we can show that this one is supplementary with that one and that equals that. So therefore this is concyclic because you've got the sum of the opposite angles is 180. So you can set that out like that. I mean, there's a lot of ways to answer this question. This is the way that I went. Part C. So for this one, we just need to think about R as being composed of a vertical part and a horizontal part. And we've got to work out which one of these angles is theta. So I would think of it like that's the same as that one, because those 2 lines are parallel. And then that is 90 minus that one. And then that's 90 minus that one. So this one has to be the same as that one. So that's theta in there. And that makes it so that the 2 sides are, because the hypotenuse is r, so this is r cos theta and r sine theta. So because this particle isn't going to be like falling down or anything, we want this force, the upwards force, to balance that one. So that means r sine theta equals mg. And then we're going to have that this force, the r cos theta, that's going to be the mass times the acceleration. And then the acceleration, well, you should probably just memorize that that's w squared r if you've got a rotating thing. I actually have forgotten that entirely, but I did remember that it was v squared on r, and that v is w times r, and then I worked it out from that. But anyway, so we have these two equations, and then we've got to work out how to turn these into this, so which can be a bit confusing at first. You know, you've got thetas here and r's, and it's like, how do we get rid of those? So the way that I thought about it is that I looked at this and saw that there was an h in it. So how are we going to get h involved? Well, you can see that you've got h and r here will give you tan theta. So you can do tan theta as opposite over adjacent. So what we could do with these two equations is just divide them. Like, this is equation 1 and equation 2. If you do equation 1 divided by equation 2, then on the left you've got r sine theta divided by r cos theta. The r's are going to cancel, and then you've got sine divided by cos, which is tan. And then on the right you've got mg over w squared r, and then the m's cancel. And then tan theta, as I said, is r divided by h. And then you can just rearrange this to find w squared. So just multiply both sides by w squared and divide both sides by all of that, and that gives you gh over r squared. Part 2. So for this one, we want to think about the horizontal and vertical components of n and t. So n has this horizontal part and a vertical part. We're going to work out which one of these angles is theta. So the way that I thought about it was that this is 180, and then this bit's 90. So that plus that equals 90, and also that plus that equals 90, so that one has to be the same as that. So that's theta in there. So n is like, the hypotenuse is n, you've got theta there. So the horizontal component is n cos theta, and the vertical is n sine theta. Now for t, you've got that angle is the same as that one because they're alternate angles. So for t, t is the hypotenuse, theta this there, you've got t cos theta is the vertical, and t sine theta is the horizontal. Now what we can do with that is to say that those two vertical components, they have to balance out the gravitational force, because the particle isn't being accelerated up or down. It's just going round and round that way. So the sum of these two, the n sine theta plus the t cos theta, that's got to balance out the gravitational force, the mg. And then we can look at horizontally. What's going to happen is that the combined force of those is going to provide the acceleration for the particle, and we know the acceleration is w squared r. So we can go, but we have to keep in mind that the n is pushing the particle outwards, whereas the t is pulling it inwards. So it's going to be the t sine theta minus the n cos theta. That's going to equal the mass times acceleration. So mass times w squared r. And let's actually use w squared from part 1. So that times r is going to be gh over r. Now we need to take those two equations and solve them for n, because we want to work out what n equals. So the way that I thought about that was that we want to use like the elimination method for solving simultaneous equations. So what we could do is do this equation times the sine theta and this equation times the cos theta, because, and then subtract them, because we want to get rid of the t's, because there's no t's in here. So if I go equation 1 times sine theta minus equation 2 times cos theta, that's going to give us n sine squared theta, and then we're subtracting a negative n cos squared theta, so that's actually going to give us n on the left hand side, because sine squared plus cos squared equals 1, and the t's are just going to disappear. So that's really great. That gets rid of the t's and all of the sines and coses on this side. And then we've got mg sine theta minus mg h over r cos theta. And that's going to make mg sine theta minus h over r cos theta, which is what we wanted. Part 3. So I've just included the result from part 2 in here because we're probably going to need that. Now the key to this question is that the normal force cannot be negative, because a normal force is pushing outwards from an object. It doesn't pull in. So we can just say n is greater than or equal to 0. And so this bit has to be positive. So we could say sine theta is greater than or equal to h over r cos theta. And then if you remember that tan theta was r over h, so we could say that h over r, because tan theta is sine theta over cos theta, this is going to be cos theta over sine theta. And then what we could do is multiply both sides of this equation by sine theta. So we'll have sine squared theta on the left and cos squared theta on the right. Now normally you'd have to worry about whether sine theta is negative or positive. In this case it's going to be positive because the theta is just like this angle here, which is going to be between 0 and 90. Like you can't have more than 90 degrees, otherwise the cone would be folded in on itself weirdly. So you could say, just to justify this fact, you could say that theta is between 0 and pi on 2, therefore sine theta is greater than or equal to 0. So that's what allows us to multiply both sides of the equation by sine theta. Okay, and then what we could do is take the square root of both sides. So that'll give us sine theta greater than or equal to cos theta. Now, again, normally this would be plus or minus cos theta, but because we know that both of these are positive, because we're in that quadrant, we don't have to worry about that. And then we could just divide both sides by cos theta. Again, we don't have to worry about cos theta being negative, so that'll give us tan theta on the left and 1 on the right. And then when tan theta equals 1, that's when theta equals pi on 4. So that'll give us theta greater than or equal to pi on 4. Alright, that's it for number 14. So stay tuned for question 15 and let me know if there was anything in this video that didn't make sense to you, or if you still have questions, just leave a comment below.